Just follow me. Follow me with something here. Take this expression here, and I want you to convert to exponential form. So peep back if you can't remember how. So convert this to exponential form. Something moves, it's kind of sorry but not sorry. Something else moves, something disappears. What moves? B goes over. Because B goes over, Y goes up. Log disappears, so you should have B to the Y equals X. Correct? Now what I'm going to do is what we call take log of each side. So I'm just going to physically write a log on each side. So mathematically, can I do that? Why? Bless you. Because I did it to both sides. So it's just like putting a square root on both sides, squaring both sides, putting a sign on both sides. As long as I do it to both, I'm fine. Now we have an exponent law, or a log law, I should say, that deals with exponents. What does the log law about exponents say? I can drop it in front. So this is going to become y log b equals log x. And then if I want to isolate y, what can I do with log of b? Divide. So I get log of x over log of b. You still with me? Probably not why we're doing this, but you're with me with the math that we've done. So if we look at what y was originally equal to, and we look at y is equal to now, we get that log base bx equals log of x divided by log of b. Log base bx equals log of x divided by log of b. If we go back to this step right here, when I took the log of each side, I chose a base of 10. Did I have to choose 10? No, I could have put any bases I wanted as long as both sides were equal. So I could have chose this to be a 3, for example. I could have done log base 3 on this side and log base 3 on this side. What would I have come down to here if I'd put a base of 3? Log base 3x divided by log base 3b. Well, what if I'd chosen log base 27? What would I have ended up with here? Log base 27x over log base 27. Well, what if I'd chosen a base of pi? What would I have ended up with here? So I'm going to stick a little n in here because the base can be anything we want it to be. So log base bx can be log base nx over log base nb. This is called change of base theorem. Why is it called change of base theorem? Because I changed the base. I took a log base b and eventually ended up changing it into a log base whatever I wanted it to be. This becomes important because your calculator is only programmed to do log base 10. So find your log button, which you've probably stared at for the last 3 years. Didn't have a clue what it did. You might have pressed it and got some weird decimal and thought, oh, well, that's no fun. So where is the log button? Someone describe its location. Right under x squared. Well, there's no other base the calculator can do. If we were to hit this, it opens the bracket right away. There's no way to put in a base unless you have the new operating system, so you might have got like a little subscript. Just ignore that for a second. The old calculators, or most of them, are programmed that you can't put in any other base, so that's why we need change of base theorem. So what it allows us to do is now evaluate logs on our calculator. So example, log base 6 of 8. Well, let's talk first, what is this asking us? What does this mean, log base 6 of 8? Without the words, it's asking. So 6 to the what equals 8? Well, is that going to be a whole number like the questions we did on Thursday? No, there's nothing whole number. 6 to the 1 is 6. 6 to the 2 is 36. So we can't just do this one in our head like we did the other ones. That's why we have change of base theorem. Change of base theorem says you can take any base and change it by putting the power or the number up and the base down. So this is going to equal log base n8 over log base n6. Power goes up, base goes down. You can put whatever you want for n. It doesn't matter. You can use absolutely any number, but what is the best number to use for your calculator? The default, which is 10. So log base 6/8 equals log of 8 over log of 6. That's change of base theorem. What does it do? Let's just use our calculator. So if I want to calculate log base 6/8, I'm going to put log of 8, close off the bracket, divide by log of 6, close off the bracket. Now, if you've got the new operating system, it should have given you a little subscript. Does anyone have that? Okay, so if you have that, you can go right to 6 and 8. You don't need to go through this step. Hit enter. Oh, don't hit enter. Don't put a negative at the end. Did everybody get the same thing? Now, we know it's got to be close to 1 because we just said 6 to the 1 is what? 6, and 6 squared is 36. So is 8 closer to 6 or to 36? So closer to 6. So usually we go to 3 decimal places when it doesn't say otherwise. So this is 1.161. Purpose of change of base theorem is just to be able to do these on our calculator when we can't do them in our head. Log base 3/5, what is that asking us? 3 to the what equals 5. Okay, so it's got to be bigger than what, but less than what? Bigger than 1, less than 2. Closer to 1 or closer to 2? Okay, give me an estimation. 1.4. Like half of you are not even awake this morning. Change of base theorem says I can put in any base for want. We're going to use our base of 10 for our calculator. So this is log 5 over log 3. Again, power goes up, base goes down. And we get, not a bad estimation, to 3 decimal places. To 3 decimal places. To 3 decimal places. 465. Questions so far? So how do they do it before a calculator? Well, 3 books I'm going to pass around. This one somebody brought me from some really old library. I don't even know where they got it. Oh, it might be Red River because it says that. I couldn't actually find a date, but the preface was written in 1865, which I'm pretty sure this is a reprint because this doesn't look that old. But here's log tables. This is how they used to do logs way back when. Through to the back, you'll see different exponent values, and if you go way to the back, so this is how they did it for a calculator. 56, so gotten a little bit smaller. They just squished more onto the page. Okay, so there's a bunch of roots. Logs are in the front. Integrals when you get into calculus. This is actually my grandfather's. He went to University of Manitoba to do engineering when he came back from the war. And so you can see it eventually got smaller over time. Now we have calculators to do all this for us. So that's what they used to have to lug around instead of a calculator. But the more you did that, the easier it would become, right? It's probably no more than you grabbing your calculator and punching it in, because once you know where the table is, you know what you're looking for. It's there. Okay, log graphs. So we looked at them very, very briefly when we first introduced logs and log laws. Now we're going to go back and look at transformations and domain and range and all that good stuff. So sketch the graph of y equals log base 4x. How do we sketch a log graph? Kind of, yes. The base to do what? We're going to do the exponential function and then take that and inverse. So the exponential function is just that 4 to the x. And we'll do it with table of values. If we put in 0, If we put in 1, if we put 2, so too big, what if I come to negative 1? Quarter, and negative 2, 1/16. So again, don't get too caught up in those little numbers. It's going to approach the x-axis and flip up. Because I know we're going to do a log graph right away, I'm not going to draw that asymptote because I know it's got to flip anyway. Okay, so going to the log graph, 0, 1 is going to become 1, 0. 2, 4. Negative 1, a quarter. Okay, so we know it's going to approach the y-axis and swoop to the right. And where would that asymptote be? Kind of? Yes, sir, on the y-axis. Okay, so that's just bringing us back to what we did before with log graphs, nothing new yet. Intercepts. Unless there's transformations that move it up or down. Why not? Because we have an asymptote at something 0, kind of. Y can't be 0. Remember, for an asymptote, we do the not equal to. Domain? I didn't hear the middle part.
No, for that asymptote, it's next to 0.
Okay, you want to change this one?
0, then x is 1.
Okay, confirm. Okay. Domain?
X is greater than 0.
Or equal to? Or equal to?
No, it's just greater than 0, but can't be 0.
Okay, range. I see some confusion on this. Let's go back and talk about it. It's a vertical line, so it's got to be x not equal to. When is y not equal to 0, the asymptote? With the exponential function. So this would be for exponential, but because we flipped to a log graph. Because I missed the wrong point. Thank you. Better? Perfect, thanks. So these can undergo transformations just like every other function. Outside brackets. Outside brackets is. Inside brackets is. Horizontal, so just like normal ones. Just note is there's imaginary brackets here, so they should come right after the log. We just get lazy and tend to drop them. So it's kind of like the sine and cos ones. Anything inside the function is going to be horizontal. Anything outside on the edges is going to be vertical. Okay, so what is A? What does it represent? The base. C, outside brackets or inside brackets? Outside, so that's vertical. Multiplication or addition, subtraction. So it is a vertical, stretch or compression. D, inside brackets or outside brackets? Multiplication or addition, subtraction. H, inside brackets or outside brackets? Multiplication or addition, subtraction. K, inside bracket or outside bracket? Why is it? Oh, that should be K, thank you. Inside brackets or outside brackets? Multiplication or addition, subtraction? Okay, so our normal everyday transformations, nothing new going on here. Here's an exam question from, I want to say 3 years ago. Okay, part A asks, how are these graphs related? So that's the equivalent to saying identify the transformations. Number 2 is sketch the graph with the transformations, and then C, the normal, identify all these things. Okay, so part A, it's really just asking what are the transformations? So what are the 2 numbers that we need to deal with in part A? The 2 and the 3. The 2, inside brackets or outside brackets? Offer of horizontal compression? Mapping? Confirmation? The 3? Y to the left. Perfect. Base graph. Okay, so the base graph is just log base 3x, and what do we use to draw log base 3x? So how do we draw a log graph? Inverse of the exponential, so we'll start with the exponential. I love the way this graph photocopied. That's very odd with all the plus signs. Okay, 3 to the x, give me some points. I heard 2 and 6 and 2 and 9. I just heard mumble mumble. Again, I'm not going to do that horizontal asymptote because we're going to turn around and flip it right away. So I'll draw it vertically. Okay, log graph, give me some points. It's hard to draw a graph with 1 point. And then draw it. That's how I should teach graphing. And then kids just draw it. Okay, now if you're a point person to do transformations, you can just jot down these points. We had 1, 0. This one was 3, 1. 9, 2. And so the horizontal compression is going to make these points. Okay, so a 1/2 0, that's not bad, I can do that. What do I do with 3 1/2 and 1? Yep, so 1 1/2 over and 1 up. And where do I plot 9 1/2? So 4.5 and 2. And what do I do with these points that would have been down here that I don't really want to talk about because they're so small? Yep, just keep going. So there's going to cross through these 3 and approach the asymptote. Did you squish it in towards the y-axis? Okay, how do we do the horizontal translation? What's going to happen to the asymptote? It's going to move as well, just like with the verticals when we did before. So translations are the only thing that can move an asymptote. Make sure you're in red pen because this is our last graph. Find a friend, write down the asymptotes, intercepts, domain, and range. Bless you. Intercept. So the x-intercept, sorry, -5/2, or if you want to have it as decimal, so -2.5, 0. Just wait, there's like some confused faces, just want to make sure we're okay with that. So the x-intercept, -2.5. So it was at 0.5, and if it moves 3 back, it's going to be -2.5. Y-intercept. Ooh, where did that come from? Okay, so you can solve in for 0 for x. The asymptote. Correct? On purpose, because I'm not writing anything. Domain? Correct? Domain? Range? Weighting? Okay, so look at it. Where's the lowest value for x? So it's got to be greater than -3. Can you repeat it again? We're okay? Range? YER? Good to go, or did you need to repeat any of those? How do we get the y-intercept? Okay, so if you put in 0 for x, so you're going to end up with log base 3, 6, and then how do we put that into our calc? Log base 3, 6. Thank you, Noah, for carrying all of this. Log 6 over log 3. Other questions on that one? British video, so they say maths instead of math.